All right, welcome everybody to a whole new week. My sister's name is Kate Kearney, possibly named after the famous woman who ran Kate Kearney's cottage in the Gap of Dunlow in Ireland. I went there and I was like, "Hey, my sister's name is Kate Kearney," and they're like, "Oh, it's cool." I mean, I planned my whole trip around visiting that place. Yeah, that's nice. Don't you want us to say? I came back with a couple magnets, gave her some pens from there. Maybe a t-shirt. I don't know. Gap of Dunlow is actually a really nice bit of Ireland. So if you ever go to Ireland, it's really nice. It was pouring when I was there because, you know, it's Ireland and it does that. But it's really scenic. It's a really beautiful chunk of Ireland. So I ended up... I was planning on hiking it, but because it was like, you know, I ended up just getting a carriage ride, which is still pretty cool. Okay. You can hear him just fine. Testing. Hello, hello, hello. Okay, so we are going to continue our conversation about pipelining and about architecture today. The promised... homework assignment on or online quiz on pipelining will be given tonight. The life supports a pipeline install. So you guys get that joke now. So that's great. You haven't learned that one yet, though. That's when we get to. Probably maybe one very soon lecture actually. We get to neon. Okay, so we're gonna get through a couple more on pipelining. What happened? Tea time. All right, well that's good. Are you playing golf or are you drinking tea? What happens with the fifth parameter in the homework? I would honestly kind of probably ignore it. We'll talk about the homework in a little bit. But yeah, fifth parameters do get passed on the stack. That said, I believe the fifth parameter is the maximum height in the map, which you don't need. So I would probably just ignore it. Okay. Yeah. Well, I don't think you have to use it. We'll talk about the homework in a bit. So we are going to Yorkshire tea. Are you a fan of the Spiffing Brit? It's one of my favorite YouTubers. He finds exploits in all of my favorite games. Skyrim Necromancy only challenges broken.
Oh, we've done it. We've just cleared out the giant camp using only a bunch of crappy level 10 bandits or something. Oh, and in return we've picked up 2 giants and 3 mammoths to fight for us.
Yeah. He absolutely exploits games, and he drinks Yorkshire tea. Yorkshire Gold, of course. Yeah. Amazing dude. Okay, anyway. Enough about awesome YouTubers, and let's talk about this awesome YouTuber, because I do put these up on YouTube. Although, it's probably not nearly as amusing as the Spiffing Brit. He's incredible. Okay, so we are going to learn more about pipelining today. So, yeah, somebody needs to make a Yorkshire Gold emoji for the ACM new vid Pringles. Click to learn more. Want to use this emoji ever? Oh, there isn't a Spiffing Brit Discord server. Look at that. Well, thank you. I think you're amazing too, guys. All right, so done bit shifts and bit rotates already. Yeah, I've already done all that. So let's talk about pipelining. So to recap last lecture, inside of a CPU, it doesn't just like run an instruction and then run the next instruction. What actually happens is that it breaks up instructions into different stages, and the number of stages it's broken up into depends upon the architecture. The classical ARM pipeline is 3 stages: fetch, decode, and execute. That turned into 5 stages later on, and 7. I think the current system is 8, and there's different pipelines. It gets complicated. The net benefit though of a pipeline is that it's like having an assembly line, and so your throughput goes up. rather than having one chunk of your CPU only getting activated every once in a while. What happens is you have a lot of processes being processed, a lot of instructions being processed all at the same time, and your throughput goes up. So the downside to a pipeline, though, or one of the weaknesses, I should say, of a pipeline, is that if one instruction depends upon another. So like if one instruction writes to register 0 and the next instruction reads from it, the next instruction can't do the arithmetic until the value's been written to R0. So what this does, this creates a dependency between the two instructions. And so if you do out of order execution, and like I said, this is relatively recent, it's not super recent, but relatively recent in the ARM architecture family. It's been around in Intel for ages. Modern Intel systems will look ahead 100, 200 instructions, 300, I don't know. It's a pretty big number. And what they do is they figure out which instructions are dependent upon which. And you can view this as a dependency graph. So this guy depends upon this guy depends upon this guy. And then the CPU will pluck the roots off the trees and run those, because these guys are not dependent upon each other. And then once they've been committed, once they've gone through the write back phase where it writes the values back into the register, then these guys are now the roots of the trees, and it can run that guy, and that guy, and that guy's probably cleared by now too, and it runs that guy. But sometimes these instructions take longer. For example, if you're doing a load from memory. A load from memory can take a heck of a long time because RAM is slow. So what happens if, like, let's say this instruction here is a load. This guy is going to be sitting there stalling for a long time. So what happens is that this guy will run, and then everything else stalls, right? If this guy is running and this guy is running, there's literally no other instructions that can run right now. And so what will happen is you'll get bubbles in the pipeline. The CPU will detect there are no instructions that can run, and it will insert what's called a no-op, N-O-P. You've probably heard me say it before. It is actually it's an assembly instruction you can give. There's no point, but you can do it. You know, it's called no-op. You can do it if you want. It doesn't do anything. It just wastes a cycle. Sometimes maybe you'll do that if you're like doing a device driver or something like that. And so like the device driver is like, you know, write to RAM and then no-op, you know, 30 times and then read from RAM. You know, that's dicey because if your CPU is overclocked, then, you know, it's going to take less time. And if it's underclocked, you know, that's a really dicey way of doing like a delay. You'll see it sometimes though. Similar to a no-op, you can do a branch never, right? Branch never, I think it is. Never takes a branch. I don't recommend it. Okay, so what happens is, let's say this fellow here is a load from RAM, and that's going to give you a 200 cycle load penalty. And let's say this guy is just doing an add or something. So that guy will be out in 4 cycles or so, whatever. This guy will stall, this guy will stall, this guy will stall, and it'll go. So what will actually happen is the CPU will do the load, it'll do the add, and the CPU will insert no-op, no-op, no-op until this guy is done, and then it will send that guy in. Oh, that guy can't go in either. So this, you know, let's say that's a sub, and then it'll do a sub, and then it'll do a no-op, 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 because you got 200 cycles, because this guy can't run because he's dependent on this one, right? And so your program will just sit there and stall, like for a long ass time. And guess what? Your programs are going to be reading from RAM a lot. And so, and oftentimes you read from RAM, then you use the thing you read from RAM. And so, yeah, these, you know, you will get long series of like, just like, you know, there's going to be like 200 no-ops in a row. And so, and there's not a whole hell of a lot you can do about it. You know, it's like, you got to read from RAM at least once, you know, like, you got all this stuff in RAM, you got to read from it at least once, you know, to get going. After you've read from RAM, I mean, you can do things to make it more cache friendly, so you don't accidentally evict things from cache, you know, maybe. But what will happen is that, yeah, your CPU is actually not going to be busy a hell of a lot of the time. Right now, I am recording video off a webcam. It's live displaying the video on my screen here. It's running PowerPoint, which has a touch interface that's displaying this mouse in real time and letting me draw in real time. And I'm capturing the entire video screen and writing it to disk, which involves compression. It's going to be compressing the video as it comes off the camera, so to speak, the monitor. And all of that said, all of this is also streaming to Discord. So I'm not only capturing the screen to upload to YouTube later, but it's also capturing my entire frame buffer, and it's sending it to Discord. And right now it's only sending out a 1080p. If I change the stream quality, I can change it to 60 frames per second and 4K resolution. And you can see that my CPU usage jumps from 6% to 34%, right? From because it's 1080p to 4K is 4 times the resolution, and then I'm capturing it twice the frame rate. So I'm doing 8 times the effort now, right? And so you can see my CPU usage has now gone up. And if I switch over to my, where is, yeah. You can see that I've got a bunch of different CPUs on my machine. 1, 2, 3, 4, 5, 1, 2, 3, 4. So Windows thinks that I have 20 CPUs in this machine. I actually only have 10. I have 10 different cores, let's say. A CPU is like the chip, and inside of a CPU you can have different cores, but essentially they function as different CPUs. They have their own, cache, L1, L2 cache. They share an L3 cache usually, and they're running their own programs. And so what's happening here is that probably each one of these different cores is getting a different chunk of the video screen or something like that. I don't know how they split it up to encode, right? So maybe one of them is handling my voice, another one's handling like the upper left corner of the screen. I don't know. It depends. It could be using the GPU as well. Let's see. Yeah, it's also using the GPU. So probably it's doing the video encryption using using the GPU. So the CPU's working, the GPU's working. It's probably writing. Yeah, there we go. It's writing to the network, 4 megabits a second. Disk, it's not writing to disk, which is weird because it's should be right. 299 megabytes has been written so far. You know what I mean? Oh, it's probably writing to a temporary file. And actually, I don't know. Why is that not 302? Yeah, no, it's writing to that file. It's just not showing up on Task Manager. Oh, it's OBS. That's why. Yeah, there it is. So yeah, so OBS is using quite a decent chunk of my GPU to encode the screen, and then it's streaming it to disk, and it's using a little bit of CPU time at the same time. Discord is obviously eating up a lot more CPU time. Okay. So bubble is when the CPU has to no op during a stall due to no independent commands. A bubble, it can be caused by a lot of different things, but yes, that is a cause of bubbles. If you cannot find any independent commands, it will stall. Right? There are other sources of stalling as well. Right? But that's that's a Discord loves power. Yeah. But that's a primary cause of pipeline stalls. Another one would be if you do a branch mispredict. Right? So if you have a branch and the branch says branch backwards and the CPU guesses it's going to branch backwards, then what it'll do is it'll speculative execute this program here, but oh wait, as it turns out, it actually was not supposed to take the branch, and then all these will turn into no ops essentially. They're actually run speculatively, but when it comes time to actually write them into a register, the CPU's like, no, sorry dude, all that effort was wasted, go into the trash bin instead. So you can think of these as turning into no ops as well if you do a branch mispredict. Unlimited power, yeah. Mm-hmm. So there's different sources of stalls, but you are absolutely right that is a major one of them. So out of order execution is a way of trying to minimize stalls, right? So like basically, rather than, let's say this is instruction 1 and that's instruction 2, that's instruction 3 and that's 4 and that's 5, the the CPU can reorder these, so it goes 1, 4, 5, 2, 3. Does that make sense? That's a 4 there. Yeah, 4, 4. There we go. Do you guys understand? So rather than the natural order that it comes down the assembly, 1, 2, 3, 4, 5, the CPU will behind the scenes be like, oh yeah, that load is going to take a long ass time. So let's move this add and move this subtract up into the gap there, because we know that's going to stall. Right? I guess it's better to try and guess right than sit there and no op and not even take the chance to get it right. That is correct. Yeah. So with a branch prediction, you mean? Yeah. And branch predictors these days can be very, very accurate. So they will speculatively execute, and they're right most of the time. Right. Sometimes you get it wrong though, and then you have to poison all those when those registers come out. You're like, nope, you're dead. Nope, you're dead. Nope, you're dead. And so they get tossed into the trash rather than being able to write to the, let's say we had some adds and we had some subtracts in there and we speculatively executed all these things. When they finally come out of the pipeline, we're just like, sorry, dude, you were on a branch that didn't actually get taken. Trash, 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 trash. And so the whole pipeline has to be flushed, essentially. But if your branch predictor is good, that won't happen too often. Okay, so next topic is called register renaming, and so this is more important on Intel systems than on ARM, but it's still kind of important on ARM, I guess, if they do it at all. So let's say that you've got a loop. You got like add and set R0 1. And this is called the top of the loop, and we'll branch if less than to the top. Do you guys see this? So let's say that R0 starts at -10. Move R0 -10, and then it's going to add 1 to R0, and as long as it's less than 0, as long as the result is less than 0, then it jumps up to the top and does it again. And so add R0, R01. And so what's happening is that it's writing to R0 and it's reading from R0. And so what happens is that technically none of these instructions can take place until the previous one has cleared the queue, cleared the pipeline. Now, and there's not a whole hell of a lot you can do about that. The thing is though, like what if you were to be loading into register 0 instead from some, memory address, and then adding 1 to it, and then storing it back, and then you've got your branch or whatever, and you got your code up here. So branch always at the top. All right, and then you got you got this part. So what's going to happen is you got a for loop, and the for loop's just going to iterate across an array, adding 1 to every element in the array. It loads a variable, adds 1 to it, stores it. Do you guys understand? Do you need me to write this in C++? Right, just starting at some pointer. We're going to go through memory, reading the values in memory, writing the value plus 1 back. Do you guys need to see that in C++? You understand? And okay, so at the top we would have a add and set and branch if greater than to done. So these two guys would be up top here. Okay, so this code in C would be for int I equals 0. I is less than whatever the array size is. I++, and we'd be saying array square bracket I is equal to array square bracket I plus 1. Okay, so we're iterating across an array, loading a value from it, adding 1 to it, storing it back. So R5 is going to get incremented as well. So we're kind of iterating through an array, adding 1 to it. Make sense? So does that make sense to you guys? I kind of left off some of the loop code, but this presents a problem because what's happening here is that we're reading and writing into R0, and then when we jump up here and do it again, we're reading and writing into R0. And so this is what's called a false dependency. Right? Because one set of R0s from one loop iteration is really it's a different variable than the next time we run through the loop. You know what I mean? And so because we're reading from R0 and writing to R0, what this will do is the next iteration of the loop is going to stall because it has to wait. It has to wait for the previous run through to finish. But in reality, these are different chunks of RAM that we're reading and writing to. We're reading from this bit of RAM here and adding one and writing it back, and then we're reading from this chunk of RAM and writing it back. So there's really no dependency on them. Do you guys see that there's a room for improvement here? Right? Because if it's all reading and writing to R0 and all these loops are really tight, close to each other, then the further down iterations are going to stall on the earlier ones. Especially because this is an LDR, right? This LDR is going to be like maybe 200 cycles, right? And so the next loop iteration can't run until the previous loop iteration is finished because it's reading and writing to R0. Will the CPU just recognize that it is a false dependency if it is smart? Yes. It will. So, that is exactly what happens. So, what will happen is the CPU will do what's called register renaming. So what will happen if you have read into R0, add 1, write R0, if you have a chunk of code where it's doing that in a loop over and over again, what will happen is the CPU will actually rename the register. So rather than reading and writing to register 0, it'll read and write to register 40. And the next iteration of the loop will read and write to register 50. And the next iteration of the loop will read and write to register 42. And the next iteration of the loop will read and write to register 90. And if you're like, but wait a second, I didn't think that there were like 90 registers, you would be absolutely correct. There are more registers in an Intel CPU than you can address as a programmer. So you cannot write an x86 to register 45 on an Intel system. But and Intel's especially bad at this because Intel's got 4 general purpose registers. So Intel really needs register renaming. So what will happen is it'll be like, okay, this register 0 and this register 0, they're called EAX and things like that in Intel, but it doesn't matter. Their version of register 0 and register 1, register 2, and register 3 are used all the bloody time. And oftentimes in completely different contexts. And so Intel CPUs have to be really good at detecting when that R0 and this R0 are actually not related to each other at all. And you can do that by just seeing when there's a load, right? If they're loading from different chunks of memory, they're obviously not connected, right? So, and then it will, behind the scenes, the CPU will actually be like, okay, one iteration, you're register 10. Next iteration, you're register 50. Next iteration, and it has a list of who's available. You're register 72, you know? And so, yeah, you might have like 56 registers behind the scenes, right? And so these are called physical registers. They're not logical registers. Logical registers are what you can access in assembly, but actually in the CPU, there's usually on modern CPUs, there's usually a lot more registers that exist, and you have no way of like touching them or writing code that can access them or any of that stuff. So, and so when you can do that, you can run multiple iterations of the loop at the same time. What you can do, especially since this LDR is going to take, let's say, 200 cycles to run, you could do all these LDRs in parallel. So load into register 50, load into register 51, load into register 52, load in, because it does out of order execution, right? So it finds all the dependencies. And so what the out of order execution does is it will end up scheduling it like this. It'll do a load into register 50 from memory address R5, and then it will do a load into register 51. Again, you can't write this in assembly. I'm just telling you what the CPU is doing. Into register 5 plus 4, and so on and so forth. And so all the LDRs will get scheduled first, And then all of the adds will go, add, 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 right? And then all of the stores will go. Okay. And so they can all be done. So rather than waiting for a load to finish, you can just kind of issue all of the loads that you have room for, right? So if you've got 50 registers, you can do 50 loads at a time, and by the time you get done with the 50th one, like the first one's probably, about ready to cook, about ready to come back, hopefully. Maybe not. Maybe you still have to wait 150 cycles. But if they're all contiguous in memory, then this guy will be 200 cycles, but then the next one will be in memory, and so that one should take place pretty quickly. And so, maybe you actually will do the stores a little bit earlier to start getting those going. I don't know. The CPU will do that for you automatically. Okay. So there's nothing you have to worry about as a programmer when it comes to that. Okay. Do physical secret registers, are they used for register renaming? Yeah, exactly. So when the CPU is like, no, you're not actually register 0, you're register 90, that's register renaming, and they're only used for that purpose. And they do that because otherwise you bottleneck on the fact you only got 4 registers on x86. Oof, that is not enough to do anything. You know what I mean? So they will. There's all sorts of problems caused by the fact that x86 stems from the 1970s, right? ARM is better. 8 general purpose registers plus 5 scratch registers is usually enough to do most, general things. If you're doing matrices, it's not really enough, and so you need to learn about neon and stuff like that to do that. Loops are very common. Yeah, loops are very common. It's like, most of the programs, most of the time spent in a program is going to be spent in a loop. So, and a tight loop, the hot loop, the hottest of your hot loops, you really need those to go as fast as possible. That's where you're going to get most of the speed increase. The place where you spend 90% of your time. 10% of your code is where 90% of your time is spent. And so those are the areas you optimized. While program active, do code. Yeah. I mean, you joke, but that's what most video games look like, while true. Do game. Okay, so that's register renaming. All right. And then one more thing, update loop in Unity. Yeah, I mean, if you look at like a Qt program, I don't know if I want to get too distracted here, but like a Qt clock program. Qt clock 1, I just want the source code, GitHub. Qt quick, I don't know what that is. Source. We're starting to get into distraction territory. Yeah, but like if you look at a lot of Qt programs, like the main is just like run. The main's like that big, So. All right, so my share is squeaking. Okay. Squeak. Okay. So let's finish off talk on pipelines with the final lecture on pipelines. It's the final countdown. Okay. Hopefully you guys get that reference. Okay. So, nap time. Oh, croissant time. Nice. It's good that we scheduled that on the agenda. QBYVB. All right, so today you're actually going to learn about how CPUs actually do things. So this is a very important lecture because you're actually going to finally learn how a CPU actually does anything. So far we've been kind of talking around the edges, like this is how the memory subsystem works, this is how the pipeline works, but how does it actually add two numbers together? We're going to learn that today. Okay. And we're going to learn about how that ties in with pipelining as well. Okay. So ALU. I was going to see Europe with White singing Foreigner live in 2019, but then COVID. 2019? 2020? Yeah. I was going to go see him on a Marth in 2019, and I was like, it's a bit of a drive. It's LA. I'll catch him next time. Then coronavirus. It's I did get my vaccine yesterday. My arm's a little bit sore from that. I am a educator, and despite working out of my house, I qualify for a vaccine now. So I did get my first dose of a vaccine yesterday. It's at Men's Warehouse. So if any of you guys are tutors or work for the school in any way, then you can get your vaccine as well. You're going to see Judas Priest with your dad. Yeah. I'm sorry. It's a great scene in Watch Dogs 2 with the Judas Priest song in it. Okay. So, ALU. This is a really, 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 really important concept. So this is the heart of a CPU. Okay? This is the heart of a CPU. This squeaking is driving me crazy. All right. This is where stuff gets done. Okay? It is a single block of circuitry, as the slide says. I hate reading slides. It's so boring when people just read slides to you. But it's the place where arithmetic and logic take place, hence the name, ALU, Arithmetic Logic Unit. And so when you do an add, when you do a subtract, that takes place in an ALU. Multiply is a little more complicated because it actually does kind of this, it's got a little loop to it. I just found out that, you know how I told you that multiplies are four cycles on a 32-bit number, worst case? Technically, I think it's 5, because I think if the last bit is a 1, I think it actually goes one more cycle. But then that's only on some ARMs. On some ARMs, it's even worse. It actually processes, I think, 2 bits at a time. So it can actually be worse. Not on the Raspberry Pi, but on like really weak ARM systems. Multiplies can actually be like quite expensive. So, but an ALU is where the ANDs, the ORs, the XORs, the subtracts, the NOTs, moving things to 0, that's where it takes place. Okay? And it is one circuit that does all of that, which is really cool. Back in the day, let's see. Yeah, that's an ALU. Back in the day, let's see if I can find a picture of it. They actually had separate boards for different operations. So logic boards. IBM. Let's see if I can find what one of these things looked like. Yeah, that's what it looked like. So you can actually find these boards, I guess, still online. That's kind of cool. And oh, come on, the image was right there. Yeah, and these things could actually plug into your mainframe. And so when you bought an IBM mainframe, which you actually didn't buy, IBM actually didn't sell mainframes usually. They occasionally did, but usually IBM mainframes were not sold; they were leased. And so what that did was that it was incredibly lucrative for IBM, because what that meant was they had a constant stream of money coming in. It's the same reason why you can't buy World of Warcraft. You know, I mean, you can, but there's still a monthly on it. You know what I mean? And so IBM would sell you a mainframe, but it was at a certain amount of money per month. And what you'd do is you'd actually customize it. So you'd be like, all right, hey, IBM salesperson, these are my needs. I am the Ford Motor Company. I need to do a lot of addition because I'm the accounting department, let's say, of the Ford Motor Company. And so we do a lot of additions all at the same time. And we occasionally do subtractions. And yeah, we do some multiplies. We figure out tax rates and things like that. Yeah, so we'll do some of those. And so they'll actually customize it, you know, just to make an example, with like 40 adders. I don't think they're actually that high, but like 40 adders and 2 subtractors and 3 multipliers. And you'd actually plug them in to the mainframe, and they would be like, all right, well, the cost of that would be $5,000 a month for our mainframe, and it comes with a free IBM service guarantee, and there would actually be a service tech, like an IBM employee, assigned to you, and if your mainframe broke down, he'd come out the same day and he would fix it, They generally didn't allow people like you and me to touch it. There would be sort of an inner sanctum, and only the tech priests, like in Warhammer, could be in the room. And that was how computing was for decades. And IBM dominated the compute space because they had so much money. And then DEC came around and introduced a sort of a smaller mainframe that was more affordable, not quite as powerful, but more affordable. And then since then, more and more cheaper, smaller, more portable, your cell phone, right? Things have gotten smaller and cheaper and more portable, have taken place. But that was the model for years. And so what an ALU is, rather than having a separate adder and a separate incrementer and a separate subtractor and a separate negator, this circuit here would do all of it, which is really cool. You could probably trace out the logic on this, but I can't. I'm not smart enough to. But this is a 4-bit ALU, I think. Yeah, so it takes in 2 4-bit numbers, A and B, and then it will output 1 4-bit number. And then you put in a, you choose a operation you want to do, and see if there's a chart here. And so with the different select inputs on it, S0 through S3, which I don't see on there. If they're all low, then it just returns A. If it's all low and then high, it adds them. And so these are all the different operations you could do on the ALU, and it's a 4-bit ALU. And so if you wanted to have a 32-bit ALU, you could buy 4 of these things and hook them together with a carry bit hooked up. So, 555, the timer chip, yeah. So, yeah, so the 74181, I think that was late 70s, was it? When that was developed? It's a slice, which means you can add multiple ones together. When was it developed? Beginning of the 70s, yeah. Yeah, and so that you can actually buy a 74181 still today if you want, and that's cool. If you're doing breadboards, which we would normally be doing in this class, we're not right now. But it can do all your basic operations: add, subtract, add 1, subtract 1, and NAND, OR, NOR, XOR, shift, rotate. And if you set up a loop, you can do multiply and divide, modulus, and so you can add multiple 4-bit ALUs together to get an 8-bit, a 32-bit, a 64-bit, etc. And so this circuit here was a game changer because you no longer needed to have a separate addition board and a separate subtraction board. Although it was nice because if those things burned out, you can just pull out the board that isn't working and put a new one in, and then you've got, or if you need more addition power, you just stick more of them in. But like at the Computer History Museum, they actually have an old 1960s era IBM mainframe in operation. And it's pretty cool. There's some people still alive who were techs back then, and they come out of retirement and they come over and they pull out the logic boards and they're like, oh yeah, that chip there is, pull that one off, and they put a chip back on and they hook it back up and put it back in and get it working again. And so there's enough institutional knowledge in the retirement communities in the Bay Area that they've actually been able to keep this 70 almost year old machine running, functioning, and you can run programs on it. They have I was there with my class actually a few years ago, and I was looking at the assembly code, and the assembly code looks totally different to this because they have variable length words, right? Because IBM's ran on tape machines, and so they could have a command that was like 100 bits long or a command that was 5 bits long because they just kind of stream off the tape. Whereas on the Raspberry Pi, everything's 32 bits: add, subtract, multiply, right? So pretty much does all binary operations. Yeah. That's the core. That's the heart of your CPU right here on the screen. Multiply and divide have to be done in the loop, but yeah, basically this is it. This thing right here. It's copy and paste if you want more of them. So, and so it used to be a separate chip. Nowadays this circuit is just part of your CPU. And so this is something called a functional unit. Now let's say you have a 32-bit one of these. This is called a functional unit. A functional unit is something inside of your CPU that gets work done. And the ALU is one of them. So the ALU is a functional unit. Let's talk about the different kinds of functional units. What kinds of things does it not do? It does all the bit operations. Adding, subtracting, nodding, XOR, setting to 0. What kinds of things do you do in load store? Very good. Yeah. So you'll typically have a, where's my mouse? You'll typically have some sort of load store unit that will handle reading and writing to RAM. What else? Clock crystal. Yeah, it's not really. That's the clock crystal isn't really a functional unit. It's important. There's a lot of important things, but like as far as actually like executing a command, what other commands could we not execute if these were the only two things we had? We've been talking about integers a lot, but are all numbers integers? Float. Yep. So the third major kind of functional unit is called the Fresno Pacific University, named after our friends at Fresno Pacific University. No, wait. No, it's a floating point unit. Okay. So these are the three kind of major things here: the ALU, the load store, and the FPU. And the interesting thing is that you will have, yeah, this is what computers used to look like back in the day. You can actually have multiple of them, right? So rather than having one ALU, you can have two ALUs. And what that will do is that'll allow you to do two adds at the same time. So for example, if you found out that you have an add R0 10, add R1 20, add R2 7, add R3 -6. Let's say that you had two ALUs. Worst thing about the tablet support in PowerPoint is that it doesn't let you erase your bad handwriting. Just leaves it up there for your eternal shame. Let's say you've got two ALUs. None of these instructions are dependent upon each other, right? This one's adding 10 to R0, add 20 to R1, add 7 to R2, add 6 to R3. They're all independent. None of them have to block in each other. So if you have two ALUs, how would you think this goes down? How would you think the CPU would run these instructions here? This is called Superscalar, by the way. Superscalar means, scalar just means a number. So like, it means super number, I don't know, like 2. If you have two ALUs, it's superscalar. It sounds really neat. Yeah, it would be 2 cycles, right? Or, you know, more or less. Right, so on the first cycle, it would run these two, and then after those guys, let's say it runs in one cycle, ignoring the pipelining for now. So let's say the first cycle will run those two, and then on the second cycle, it will run these two. Okay. This does, however, require multiple issue and multiple, I can spell, commit. So the CPU needs to be able to issue 2 different instructions at the same time, and then after they finish, it needs to be able to retire 2 of them at the same time, or commit 2 of them at the same time. And usually they will. If you have a superscalar system, they will generally be able to issue at least 2, at a minimum of 2. Otherwise, there's kind of no point, right? It's like, you got 10 ALUs, yeah, but you can only issue 1 a cycle. It's like, cool. Yeah, I guess with pipelining effects, you know, it'd be useful. But yeah, with multiple issue, you can pass out two adds And they start doing their thing, and then when they finish, you have what's called a commit register, or a write back area, or retirement queue. There's different names for this kind of stuff. And basically, when they finish, they're like, "Hey, we're done." And then the retirement center takes the results and it writes the results into the register. And then the next cycle, it issues these two, and then when they finish, they both retire they write back the registers as well. So this is called Superscalar computing. Will Ferrell is a heartthrob. Yeah, not really. So, so this is called Superscalar computing, the ability to have multiple ALUs. Let's see if I have a picture. There we go. So, like, once you've taken this class, let me hide my face so that you can see the whole thing. Once you have, yeah, I guess I'll turn off, yeah. Once you've kind of taken this class, then when you look at these block diagrams of CPUs, like, they actually start making a little bit more sense. And you can actually pretend to be an electrical engineer or a computer engineer. So this is this is a block diagram for my old CPU. So I used to have a Intel 2600K, Core i7, pretty decent CPU. Like I said, I had that for like a long time, and it held up pretty well over the years. So so let's see what things we actually can understand so far. We haven't talked about buses yet, so don't worry about that. We haven't talked about translation look-aside buffers, so don't worry about that. We've talked about caches, yes, you should understand that. Translation look-aside buffer, you don't know. Retirement register, yeah, we'll just learn about that. Okay, so let's go through this. So let's say you are, does this only apply to ALUs or does it apply to other functional units? Great question. Let's take a look down here. Do you see multiple ALUs? Yes or no, Rivera? Are there multiple ALUs in yellow? Yep. What about floating point units? Do you see multiple floating point units? Down here. Yes. So there is one here that does multiplies and divides, and there's one functional unit that does adds. So if you wanted to do multiple floating point adds, you're stuck. There's only one of them, right? I think SSE, I'd have to look into that if that can do it. But you've got one that is used either for multiply or division, one that's used only for add, but you can have multiple of them. So yes, yeah, there is AVX. Yeah, this is a, yeah. So here we've got 1, 2, 3. This is only for multiplying branch. It's also SSE. So it's got like 2 general purpose ALU things, and it's got several that are done for, we haven't learned about this yet, for SIMD computing. But you can see there's, let's just say very briefly, there's 6 ALUs, right? It's kind of an inaccuracy, but there's 6 ALUs. So you could in theory do 6 arithmetics at the same time. And then there's 2 floating point things, but this one only does add, this one only does multiply and divide, let's say. So if you've got a multiply followed by an add, then these 2 things can run in parallel with each other. Okay, so let's say that you've got a command coming down the line, it's add, add R0, 10. Let's follow the life cycle. Let's follow the life cycle of an instruction. So at this, let's see if I can do my handwriting better here. Add R0, 10. Okay, so it's going to start off in RAM, and so it's going to, your program begins way off here in RAM land, right? And it's going to flow through the L2 cache into the L1 cache here. Okay, and so the first phase is fetch, right? So it's going to grab the next instruction. Let's say it grabs this instruction here out of the L1 instruction cache. It's a small cache. You can tell it's L1. Here's L2 over here. So it fetches it out of there, and this line here means that it's actually grabbing 128 bits at a time. So it's Intel doesn't have a fixed bit size for instructions, but let's say that's 4 instructions at a time, four per cycle. And so the fetcher is going to sit there and grab these things, and it's going to go into a buffer, and these things get decoded, kind of. Intel's weird. And then 6 instructions per cycle come out and go into the instruction queue. And so basically what happens is that you've got your add, subtract, you got all these things coming out into the instruction queue. And so for this one, there are 18 entries in the instruction queue, and these things will be fed to multiple decoders because it can handle multiple instructions at the same time. Intel supports complex instructions, ARM doesn't, so you don't have to worry about that. But basically, this Intel will actually rewrite these things from x86. It goes from x86 out here to some sort of like RISC thing inside of here. So there's actually an internal assembly language you don't get to see. I don't know if you guys heard that. So you would write x86 assembly, but what happens is that Intel is stuck with x86 because x86 sucks, kind of. And so what happens is that it actually will translate x86 assembly into some sort of internal assembly. You don't get to write the internal assembly. That's not available to you as a programmer. But yeah, so these things are called micro operations here. Okay, and then basically what happens is 7+ entry micro op buffer. So all these commands get translated from x86 into some sort of secret assembly that you don't get to know about. And then they are in this queue here. It does register alias table and allocator. So let's see, is this where renaming takes place? Probably. Register renaming, return register file, reorder buffer. Yeah, so it'll probably do the register renaming here. And then it will go, this is the pipeline, by the way, that we're looking at here. One cycle, one cycle, one cycle, one cycle, one cycle, right? And then this is the part where the out of order execution takes place here. Out of order execution takes place there. And as things get retired, then it keeps track of that. And then it goes into the reservation stations. So this is where the Superscalar takes place. Superscalar. Okay. And so these are all of your different functional units. Where's my mouse? So these are all of your different functional units over here. Okay. And so what happens is that it basically looks to see which functional units are available. So if you got an add coming down the line like this, we've already done the register renaming. We've done the out of order execution. Then it's like, all right, who's busy? Okay, that's busy, oh, wait, this one's available. So it'll send your add to this one here. Okay. Cycle goes by, it produces the result, and then this goes to the retirement zone. And basically, it's going to save that into, yeah, here it is, over here. So it saves the results into that. Okay. And if you do loads and stores, you can see there are loaders and storers over here. Like that. There are 2 storers, one for data, one for addresses, one for loading. This one will handle the loads and stores in intelligent fashion. And then that goes off and talks to, if you do a load, it's going to come over here and talk to RAM, and then RAM will eventually make its way back into here. Into here. And then that gets put into the registers. So that's, are these 4 different functional units, or are they considered to be one? The ALUs, they're different. And so you can have this guy, here saying x plus 5, and this one over here saying z minus 2, and this one doing like 3 plus 3. So each one of those ALUs could be working on a different thing at the same time. Oh, the load store ones? The 4 different functional units, it's I believe on this system you can only issue 1 load at a time, but basically it's going to go into this cache here, and this cache is going to be getting the results from RAM and then putting them into the registers. So yeah, you can have different you can have different functional units for memory as well. So that is how a CPU looks on the inside. This is, you guys now know enough to know most of the stuff. The translation look side buffers aren't really that important for where we are right now. You don't need to know how buses work right now. So yeah, and so basically an instruction comes in here, gets fetched, gets decoded. It's got a special x86 decoding phase where it goes from x86 to like secret assembly. Right, that's something that doesn't exist on ARM. And then after that, it does, the register renaming. It does the out of order execution, and then it looks and it'll find like some open ALU and then do it, and then write the results back. And then when you're ready to write those registers to RAM, then you use that functional unit there, or sorry, store, and then it'll get written to RAM. So that's basically what's going on inside of a modern CPU. Like I said, the point of this class is to sort of demystify what's actually happening inside of a computer, and that's kind of the big high-level picture of what's actually happening inside of your CPU. Like I said, today's lecture is pretty important. So if you have any questions about it, now is a good time to ask. The key point 1 is ALUs are where the actual math gets done and logic gets done. Key point 2, you can actually have multiple. Here, picture. You can actually have multiple ALUs. And so a CPU can do more work than just 1 per cycle. It can do 2 per cycle, maybe, right? So if you can issue 2 instructions and retire 2 instructions per cycle, and you have 2 adds that don't depend on each other, and you got the functional units available for them, then the CPU will be able to do 2 instructions per cycle. And that is that all-important IPC, right? Instructions per cycle. And so in theory, you might be able to get 2. Right, if you have a dual issue, dual retirement machine, then you can actually do 2 instructions per cycle instead of 1. Okay. In reality, you rarely get full performance. Right? Whereas the Fresno Pacific University, right here, you got 2 of them. Okay. So this one's got like 6 ALUs, kind of. It's got 2 FPUs, kind of. It's got 3 load store units, kind of. It's complicated. You can think of it that way, if you'd like. There is a limitation. There's, I believe the Core 2 architecture is dual issue, so I think it can only write to 1 of these ports. So I think it can do 2 ports. I don't know. I'd have to look it up. It's been a while since I've looked at it. I think there might be a bottleneck on the port number, maybe. I'd have to look it up. It would have been awesome to mess with logic circuits. I know. Okay, so what do you need to know about the ALU? You just have to know what it is, right? It can do these things. A plus B, A plus A plus B, A times not B minus 1, A plus not B, A plus not B plus AB. There's a lot of AX or B, A plus. There's a lot of options for an ALU. That's the heart of your CPU. That's where things actually happen. Okay. It's like silence on Discord right now. Is this too easy to understand, or is it too hard to understand, or is it just right? You don't have to make one. Like if you're worried that you're gonna have to reproduce that on the midterm. It's kind of a genius that figured that out, right? It's kind of a genius figured out. Because rather than having one circuit to do addition and a different one to do subtraction, they found areas where the circuits were the same, right? And that's crazy cool. There's 32 different operations this thing can do, right? So, yeah, genius level. And that again used to be a separate chip, and now it's just part of your CPU, and you could have 6 of them or whatever. So, I have a question for you guys. What would you do with a statistics and number crunching computer that starts at only $7,400, has 16 kilobytes of hardwared basic language, and 28 major peripherals? What would you guys do with that? Play Doom, compute p-values. Trying to look at what price that is in this was 1973, so let's look up the inflation adjusted price. $7,400. I am in 1973, and we are spending only $7,400 for a computer. That is a $44,000 computer right there. $44,000. It's got 16K of RAM. It's got a 4K operating memory. Wow, it's got 4K of RAM, guys. That is more than any person could ever need. You get a big 16 lines, like your monitor can display 16 whole lines at a time. 64 characters long. Extravagant. It's extravagant. And a keyboard. Comes with a keyboard for $44,000. You get a free keyboard. It's called Wang. Yes, it is. It is called a Wang. Yes. Can it run Crysis? Probably not. Probably not. It finally ends your dollar trade-offs. Yeah, this is not a personal computer. This is an alternative to the IBM mainframes of the time, which were much bigger and much more expensive. And you could actually own it, right? IBM would let you buy your mainframe sometimes after your lease is up. But, yeah, just try to outgrow it. Try to outgrow it. Look, 4K of RAM, you can buy more. If 4K is just not enough for you, at $1,600, it's $1,600 is like $9,000, $10,000. For $10,000, you get another 4K RAM, up to 32K. Whew. That is like you can hold your entire country club in 32K of RAM. It's amazing. You get 3 different kinds of printers and a flatbed printer for only $8,000. So for only another $44,000, you can get a flatbed printer. Have you been appalled lately by disk prices? Starting at just $20,000, we can offer you our new floppy disk. For big disk power, you can have 1, 2, or 5 megabyte hard drives. A 1 megabyte hard drive. That is the size of a floppy. Floppy goes up to 0.75, and then your hard drive is a meg. Big disk power, yeah. Yep. So, yeah. Even if you call the Wang System 2200 a small system, you have to admit it's a big idea. So, there you go. Big disk energy, that's right. How much was it IBM mainframe? It depends. Well, there's actually a very funny story about how IBM priced their mainframes, which may have some relevance to you guys. The fact of the matter was, like, when the computer revolution was taking off, and this is before my time, my dad told me about this. When the computer revolution was taking off, nobody really knew how to price these things, right? Like, you know, you go to Ford and you're like, hey, we can sell you a mainframe. It can do all of your accounting for you. So you can have all your numbers in there and write it to tape, and have backups of all your accounting and make sure you don't have accounting mistakes and stuff like that. And Ford's like, all right, that sounds good to me. How much is it? And so IBM would say, oh, it's $5,000. And if the Ford person doesn't blink at that, they say a month. And then they kind of narrow their eyes. But for an important customer like you, we will knock that down to $4,000 a month. And they go, And so they just sit there. The salesman had literally, there was no frame of reference. Like, nobody knew how much computers should cost. And so what they do is they just throw out a number and see if the people flinch, or like, if they don't react to it, the price goes up. If they go, then the price goes down. And they would just sit there and just like watch the facial expressions of the the people on the other side to figure out how much they were supposed to charge for these things. Even at 5 megabytes, you need 53,000 of them for one Call of Duty Warzone. Yeah. Plenty. Just try to outgrow it. Oh, let me introduce you to Call of Duty. Let me introduce you to a patch for Call of Duty. They give free programming schools. That's neat. That's neat. They have a program library for stats and math. That's cool. One user group with the unlikely name of Swap. I don't know why that's unlikely. Our user group with the unlikely name of Swap could help you cut programming costs even further. We do a lot for you here at Wing. So, just the patch is 20 to 50 gigs. Yeah. So yeah, no, so there was no like fixed price on it. They would just sort of toss out a number, and then they're like, okay, now let's talk about peripherals, right? And then they would throw printers on top of it and stuff like that. And if the person's like, wait, there's peripherals on top of that. Hey, but for you guys, we'll throw it in. And so there's just, they would just sit there and just figure out what they could do to squeeze, as much money out of it as possible. It was a very successful business model. They, IBM was the dominant computer company in America. So much so that they had antitrust people looking at them. So when the PC took off, which was made by IBM made the personal computer. That's what it was called. It was called the IBM personal computer. They were the company that made it. They had Intel make the chips, and they had Microsoft, among other companies, there was CPM also and some other ones, make the operating system. IBM actually could have bought Intel reasonably, and they could have bought Microsoft for sure, and then had everything be in-house. Right, but as it turned out, that would have probably caused IBM to have been exploded by the federal government. And so instead, what happened was Microsoft became a international titan. Intel is perhaps has its glory days behind it, but Intel had a pretty good run of 40 years or so of being one of the world's biggest and most powerful companies. And then IBM sort of faded into obscurity. They ended up reinventing themselves as a consulting company in the 90s. They still make IBM mainframes. It's still a thing. But the one at the Computer History Museum, I believe it was the mainframe for Country Club. IBM mainframe price. IBM still sells it, all right. How much does an IBM mainframe cost? Whatever you'll pay for it. Entry level starts at $75,000 today. Okay. Yeah. Costs millions to rent or get one. Yeah. So. Yeah, it's kind of cool. Like the Computer History Museum, we had a field trip planned last 2 falls ago. They got canceled because we couldn't get a bus. Chris is here; he can tell you about that. And then it got rescheduled for last spring, and then COVID hit, and we didn't get to see that. But let's see if I can show you on an old school. Yeah, there you go. So basically, this is what an IBM server room would look like, and it'd be on raised floors. There'd be cooling beneath it, and they didn't allow random people in here. You had to be a trained IBM, person either working for the company or having gone through their training in order to service the thing. It's like you're a tech priest from, like I said, from Warhammer. And so this is a System 360 classic mainframe. And so they'd be in these specially, you know, air conditioned, and there would be usually fire suppression systems. I don't know if you can see it. Yeah, that's just water. That's not a good idea. There usually be like some sort of halon release if there's a fire, because these printers would catch fire sometimes, right? So oftentimes your printer would be in a different room, because these line speed printers, these things here, this is a small one. The big ones, we actually had one at my college, and man, those things could shoot out paper so fast. Like, it was about this big, like you can't see it, but it was like this big, the paper. And what they used it for is for printing source code, because they used to grade source code by hand. And so what they would do is the entire class, like 300 people, would submit their source code, and then the printer, high-speed line printer, would shoot all of the students' code out, and then the thing came out of the printer so fast it actually flew into the air. Like, the paper was actually coming off in the air like this, and arcing down and folding itself into boxes. And so they go shh. But if any friction built up, or little paper, you know, like little paper fibers built up, heat would build up and they would burst into flames. And so they were in their own fire isolated room with a fire suppression system on it, because they would occasionally burst into flames. And then what happened is you'd come in and get this box of source code, and you'd hand it out to your TAs, and the TAs would go through with a red marker and mark people's code up. And if they didn't like your variable name or whatever, you'd lose a point. And that was how, you know, grading was done at my institution. And it was archaic even for, you know, the mid 90s when I was there, mid to late 90s. Muya has posted a fight within a server room or something. Yeah. Anyway, it's kind of cool. Like, you know, I've been in these rooms before, and it's kind of a neat experience. You know, you can see all the magnetic tape here that's used for backup. That's a little line printer there. So, it's kind of important to know history, because it actually kind of explains a lot about the modern day. You know, when you understand history. You know, why does x86 have only 4 registers? Why? Yeah. Why is IBM a has-been? Because they were too strong, is why. And so the federal government kind of stopped them from getting stronger, for better or worse. I'm not really sure if Microsoft being a dominant player was a good thing in the long run. I don't know. They use halon gas to protect the art pieces. Yeah. And so when you're in one of those server rooms, they actually tell you, like, if the alarms go off, run over and get an oxygen mask, because you will die. Because the fire suppression system, so there's big flashing lights, and you run over and you grab an oxygen mask, because you will die if the halon goes off and you breathe it. So cool. It's exciting. Adds excitement to your day. They take kids through there. Yeah, still find IBM stuff in central offices. Fun walking through. Yeah, I think so. There's something neat about, like, supercomputer centers and stuff like that. It's one of the reasons why I specialize in supercomputing. It's just because messing around with these giant machines is kind of fun. So the Computer History Museum, I don't know if this will ever happen. It seems like it's cursed. But the Computer History Museum, if you get a chance, closed until summer. Okay, cool. They have an operating IBM, like I was telling you. Let's see, oral histories, that's cool. IBM 1401. PDP, yeah, so this is a classic machine here. You can actually play video games on it. Johnson, were you on that trip? The first one? Is he still here? Did he leave? Oh, he's muted. There you go. No, yeah. So, we were all on the bus, and we're like, wait a second, we did a head count and one person's missing. And so, really, CHM, you're doing this to me? And so I ran back because we had we went to two museums. We went to the Computer History Museum, then we went to the Intel Museum. And I ran through the museum trying to find the missing kid, and he was a kid. He was still a high school student. And we're like, oh, damn, we just lost this kid, you know? And I found him in front of the PDP-1 playing video games on it. I think they had Space War loaded. Yeah, they had Space War loaded up on it. And he was sitting there playing it. And I'm like, dude. Dude. All right. Yeah, but the IBM mainframe is pretty neat. And you can still program it and run it and stuff like that. And that has the discrete logic boards on it and stuff like that. So it's when was this made? Early 1960s, yeah. And so this was made before they really had integrated circuits, which allows you to repair them. So you can actually, if you find an adder and one of the AND gates burns out, you just replace it with another AND gate, and it works. And so one of the neat things about the old computers is that because they have discrete logic boards, you can fix them. Whereas if you had like an old Pentium, if there's a power surge and part of the Pentium chip burns out, it's dead, right? You're not going to be able to take the casing off and get an electron microscope and figure out which logic gate is dead, right? But on an old IBM mainframe, you can actually sit there with your multimeter and figure out what died and tear it apart. And several faulty circuit cards were found and required. All in all, 130 cards were located and fixed. So they found a IBM 1401 that had been running nonstop for 23 years, from the 1970s to the 1990s. And so this thing had actually been in service for a long time, and then they bought it, I think, on eBay and transported it across the country to the Computer History Museum. It's a cool thing. It's cool stuff. Computer history is neat. Okay, so is Space War the oldest game? Maybe. Maybe. I'm sure people have been making games since the beginning of time. Okay. So ALU, FPU, load and store. So the 2600 can issue up to 6, and it can retire up to 4. Okay. So it can issue up to 6 instructions per cycle and retire up to 4, but they can't all be the same because of those limitations that I was talking about. So this is again one of those things where the architecture is you want to read the data sheet and figure it out. And does this matter to you? Okay, so what I talked about earlier was like out of order execution. Does that matter to you? Does Superscalar matter to you? Does pipelining matter to you? And the answer is kind of. If you're writing assembly code and you're trying to squeeze the absolute max performance out of something, if you know that your CPU does out of order execution, that means you don't have to worry so much about moving things around yourself. If your CPU does not do out of order execution, then you do. But in general, I think our the Raspberry Pi server does it, so you don't have to worry about that. But things like Superscalar, yeah, that's actually really neat to know, because I sat there and redid some of my high performance code over and over again, trying, all right, let me do 2 loads at the same time, let me try a load and a read and a store, and I sat there because I knew that it was Superscalar, and I think the Pi is 2 issue and 2 dispatch, something like that. I don't remember off the top of my head. And so I sat there and tweaked my assembly code to squeeze every absolute ounce of performance out of the thing that I could. And I got it able to run a Photoshop filter on a 4K image at 30 frames a second, which is pretty damn good. Using the CImage library that what you guys used in CSI 40, it was 8 seconds to do 1 frame. So by tweaking it and tweaking it and tweaking it, I was able to get it 240 times faster. With O3 on, I think it went from 8 seconds to 1 second. And so I was basically able to get it 30 times faster than what the optimizer was able to generate. So, and that was only possible because I knew about pipelining, I knew that this instruction the result from it would be ready down here, and I spent hours just sitting there just like tweaking it, and I was able to get it 30 times faster than O3. So it's pretty good. So yeah, this is, in general for C++ kind of stuff, it's sort of invisible, and it's invisible most of the time, but if you need to squeeze performance, you kind of do need to know how the CPU runs. The 2600K can have 100 simultaneous memory operations going on at a time. It can have sort of 64 assembly instructions kind of in flight at once. So usually that's not possible if you're just doing basic things like adding and subtracting, because maybe, yeah. But yeah, it's this changes every generation, right? How big is the window that it's looking at for reordering instructions? I think it's up to like 250 now, something like that. So all these things change every generation. How big is the cache? How many secret registers do you have? All that kind of stuff. All that changes, and that's why CPUs, every generation, they get a better and better IPC value, because they tweak those numbers and they make caches bigger and things like that. And they're able to do that despite Intel not being able to move to the next process node. That for years, we were shrinking the CPUs and shrinking the transistor sizes, which allowed us to put more things on it. We can get more cache. We can get bigger and bigger everything, and because things are smaller, you can usually run it at a faster frequency as well. When things get closer together, you can run it at a faster frequency because there's what's the name of the effect? I'll have to look it up. That allows you to run at a higher frequency when things are smaller. But that's kind of stalled. Intel especially has stalled these days. It's become very, very difficult to miniaturize things anymore. TSMC seems to be the only company right now that's actually on top of the ball with it. 10 years ago, there were 12 companies or so that were doing cutting edge fabbing. There used to be AMD. AMD was in the business with Global Foundries. Who are some of the other ones? Now it's down to 3. Now it's down to Intel, TSMC, and Samsung. Those are the only 3 fabs left that are actively pursuing the smallest, nanometer sizes. And of those, TSMC is the only one that's succeeding. So it might be down to 1, right? Which, would be an interesting world. 20 years ago, there were 20 or 30 companies that were doing fabbing of silicon, semiconductors. And then 10 years ago, there's 12, and now there's 3. And maybe 10 years from now, there'll be 1. Maybe TSMC will be the only company in the world that can do cutting edge stuff. But part of the reason for that is because, like, if you make a new chip on a cutting edge fab, the lithography is like the big cost of it. You're talking $70-80 million. But if you use an older generation, because older fabs are far more common and cheaper, and they're established and known quantities and stuff like that. If you use an older, like, do you guys understand what I'm talking about? Like 7 nanometer versus 20 versus 50 nanometer. It's the size of a transistor basically on it. Like anyone besides Alan? Are you guys just mystified? Am I talking nonsense, or because what does this impact you guys as computer science people? Well, for one thing, CPUs are kind of stalling. CPUs aren't getting a lot faster these days. GPUs are doing really well. CPUs have not been doing well. So what does that mean for you guys? Well, maybe you should learn how to program a GPU, right? Like that, you know. If you look at the difference in performance from 10 years ago, a GPU 10 years ago to a GPU today, it's a night and day difference. Night and day difference. Whereas you could use a 10-year-old CPU and you'd probably be fine. Like I said, I used my 2600K for 8 years or something. It was fine. Like I never noticed it was an old CPU. So that's one area where that can impact you. So maybe you guys might want to take my game development class, because I'm planning on doing CUDA with it. And I've got my book on here somewhere. Somewhere. I bought a book on learning to program with CUDA, and so let's learn how to program GPUs, right? Why is CPU tech stalled? This is the problem. So what drove CPU performance gains for years was Moore's law, right? Like the number of transistors on a chip doubled every 18 months, and the clock speed went up, you know, by a factor of 2 every 18 months, something like that. And what's happened is, as we've gotten, I'm saying we as if I have anything to do with it. I don't. This is how big the feature sizes are on a chip. These are nanometers. These are really, really, really small, right? And so you can see how, as things get smaller, the density of transistors goes up, right? And so this is driving, you know, the more transistors you can have on a chip, the bigger the cache size, the bigger the look-ahead buffers can be, things like that. The problem is that this, once you start getting down to these things, it gets really hard to do the lithography. Lithography, again, is you're essentially doing film development. You've got a photoresist on a surface of silicon. You trace a laser on it. It develops the photo. You use the acid to wash away everything that is not developed. There you go. You got a line that you dope separately with positive and negative ions, and that makes a wire and semiconductors and all that kind of stuff. It gets really, really hard to go this small. And so what happened was, like I said, 20 years ago, you had 20 or 30 companies that were making things, and as it got smaller and smaller, it got harder and harder, and companies started giving up. AMD gave up. Global Foundries announced they're not going to pursue smaller feature sizes. They can't. And Intel has been trying to move to the next feature node, the next node down, for a long time now, and maybe this year they're finally going to hit it. And TSMC is already announcing they are building a $20 billion foundry to build 3 nanometer. So that was actually just announced very recently. So TSMC is, I don't know, 2 or 3 generations ahead of Intel at this point. And part of the problem is that as these things get smaller, the cost goes up exponentially as well. So as the feature size gets smaller, the cost doubles every 18 months as well, right? And so what has happened is that very few companies have the willpower or, you know, really money to do it. You have Samsung, Intel, and TSMC, and so, you know, that's it. You know, so yeah, $20 billion to build a factory, right? So when Intel 20 nanometer came out, it was the other way around. Yeah, Intel 10 years ago was just cleaning AMD's clock. You know, they were eating everyone's lunch, and, you know, they haven't had a good decade. Let's just put it that way. So Intel's going to have some of their manufacturing move to TSMC because they're having trouble figuring it out. So, yeah, good news for Taiwan, I guess. You know, because the T in Taiwan, T in TSMC is Taiwan, right? So, from like a geopolitical standpoint, that's really good for Taiwan. There's a reason why we have a carrier group there right now. You know what I mean? It's like the world is dependent upon TSMC, right? Automotive, you know, production is slowed because Ford and all these other companies can't get enough chips out of them. And so we have a carrier group sitting there because China's been kind of saber rattling over Taiwan, got a new president. So, you know, we have a carrier group deployed to Taiwan, I think, Maybe because of TSMC by itself, I think would be enough of an interest. You think oil was important 20 years ago, right? How important is the only source of high-speed chips in the world, right? Not like they're making them there, right? Like I think the new foundries can be in Texas or something like that, but yeah. It's, from a geopolitical standpoint, that's, you know, really big news. It's really important. So, poor Taiwan. Well, you know, believe me, it's good for them to have TSMC there. Yeah, the world will not allow them to be invaded and risk losing that company. So yeah, so our Raspberry Pis are a dual issue, so they can issue 2 instructions per cycle. Leverage over China, yeah. It's a, you know, from a strategic standpoint, it's good for the country. Did I say country? Yeah. So if you have a 900 megahertz CPU, then in theory you can do 1,800 instructions per second. Does that make sense to you guys? So if you have 900 million, clock goes up, clock goes down, clock goes up, clock goes down. If you've got 900 million of those a second, and you can do 2 instructions per cycle, then in theory you can do 1.8 billion instructions per second. Right? And there's all sorts of tricks you can do to actually squeeze more performance out of it than that. In reality, though, you don't get anywhere near this kind of performance. Yeah, let's not worry about bit packing for now. So let's talk about the homework, because I promised you I'd talk about that. So I put together a demo for you guys that might help you a lot. If that's the wrong server. Put together a demo because I thought it would help. All right, so let's say you wanted to access a 2D array, like in your homework assignment. The hardest thing about the homework assignment is grabbing the right value at the right location. Once you can do that, this homework assignment is not hard. Okay, because all you do for this homework assignment is, let's say you're at row X, column Y. All you do is, if you're at row X, column Y, you grab the value there, and then you grab the value at row X, column Y plus 1, row X minus 1, Y plus 1, row X plus 1, Y plus 1. So you grab 4 values. Your elevation, and you grab the elevation of the 3 people to your right. East, northeast, and southeast. That's it. This is not Dijkstra's. You do not have to do pathfinding. All you have to do is load 4 values from the array. Your location's elevation, and the elevations of the 3 people to your east, northeast, and southeast. And whichever one is closest in elevation to you, you move to that spot. You set the elevation to -1 to indicate that you have moved there, and repeat. And you start at the left column, column 0, you go to the right edge of the map. That's it. And so the hardest thing is that row major ordering. That's why I'm having you guys do this, is because you need to internalize the ability to do row major ordering. And so what I have here is, I just typed this up during office hours before class. So if we had in C a function to print an array that basically said, for every row, for every column, print, you know, that row and column. This is the row major ordering formula, right? It's row times the number of columns plus what column you're on. Do you guys understand this is the formula? We don't have a 3D array, so there's no planes. It's just, do you guys understand this algebra right here? It's a mapping between a 2D array and a 1D array. We do this all the time in high performance computing, and it's important to get down. Okay, so how do we do this in assembly? So we've got a doubly nested for loop. So doubly nested for loop is going to look like this. I got the outer loop, I got the inner loop. I start off by just, remember whenever you have a function call, I always move the parameters out of R0, R1, R2, R3, because those things get destroyed, right? If you First time you branch with link, all those values get destroyed. Don't leave your stuff. It's like leaving a bike on the sidewalk in Fresno, right? Like it'll stay there for a while, but it's probably gonna vanish, after a certain period of time. So I immediately move all of my stuff out of R0, R1, R2, put them into real registers, right? Make sure you do that. You know that, the pushing and popping, all that. So I first back up the parameters, and then I just have a doubly nested loop. So I start off by initializing it to -1 instead of 0. Reason for that is I add 1 immediately. So I'm just adding 1 at the top of the loop. It just simplifies the logic a little bit, rather than doing the plus plus at the bottom. This way I don't need 2 branches, I guess. It makes the logic a little easier. You don't have to do it that way if it bothers you. So I start off by initializing both I and j to -1, and I immediately add 1 to them at the top of the loop, just to simplify logic a little bit. And then, let's see, I compare I with the number of rows, and if we've hit the number of rows, we're done. If not, then we do a loop of the inner loop. And so this is just a standard 2D, doubly nested loop to print a 2D array. So let's get to the meat of it. Here's the meat of it. You guys don't need to use the MLA command. Yeah, forgetting to multiply by 4? Yep. I know I've talked about this twice already, but yep. Guess what I did when I wrote this originally? I didn't multiply by 4. And I was getting really weird results. And I'm like, what the hell, dude? What am I doing wrong? Oh. Yeah. Yeah. Everyone does it. Everyone does it. Multiply the number, the index by 4, because then it's 4 bytes. Okay. Everyone does it. The MLA command, you don't have to use that. You could do a multiply command, then an add command. MLA is just it's 1 command instead of 2. It saves you a cycle. So MLA is of course contrasted with the APA citation formatting. It also stands for multiply and accumulate, which means multiply and add. So what this actually takes 4 parameters. If you see that, it's a little unusual for ARM32. Not alone, but a little unusual. And it will multiply R7 and R6 and add R8. So it multiplies R7 and R6 and adds R8 to it. So that's why it's there, because we do this all the time. Matrix math uses multiply and accumulates, and array indices use multiply and accumulates, and so it's just an easy optimization. It's 1 multiply. Essentially, the add is free. It'll do the add for free. If you don't want to learn it, if you want to purge it out of your brain and just do a multiply followed by an add, knock yourself out. Like I said in this class, the important thing is just getting it to work, and then optimize after. Optimizing is the fun part, right? Is that a pseudo command or is that 1 cycle? It is not 1 cycle. Multiplies are not 1 cycle. Multiplies are 4 cycles, or 5 as I learned today maybe. But it does the add for free. Okay, so the add is thrown in for free. The multiply, though, it's still a multiply. So it's still 4 cycles. It's 4 cycles instead of 5. Let's put it that way. Yeah. So it's there for you. You can use MLA if you want. Multiply the if we're on array index 5, multiply it by 4 to get the byte offset, because integers are 4 bytes. So if we're at index 5, that's 20 bytes to the right of the index. Base plus offset. The base is held in R4. The offset is going to be that times 4. So it's R4 plus the offset. Okay. And then we're loading from that address in RAM. I print it to the screen, I print a space, and then I jump to the top of the loop. Come back to the top of the loop, it adds 1 to J, sees if we're done. If we're done, it jumps up to the top here, adds 1 to I. If we're done, then it jumps down here and quits. So if you want to see this in action, let's make a 10 by 3 array. 10 rows, 3 columns, and so you can see printing it in C++. I generated some random, not random, but there's a pattern to it. Some numbers, and you can see that the assembly code matches the C++ code. So that is found in 20 2D arrays, and I think the C++ driver code for that is called 2D arrays, and that is in your demos directory. And so basically just reads in a number of rows and columns. It generates an array. Generate some cool numbers. Array. I should probably delete this, huh? Shouldn't I? I'm memory leaking right now. I apologize. It's rude to leak in public. Delete R. Don't leak. It's rude. Okay. So, yep. And so all it does is it calls the function in C++, then it calls the function in assembly. Shows you it's the same thing. Okay. How is it one declares an array in ARM? Good question. So there's two answers to that. The first is if you know how big your array is going to be, then you can use the .skip directive. So that is in 12. Oh, I've got another 2D array. Damn it. Did I really make a duplicate? So unfortunate. Yeah, whatever. Vim 12 arrays. So we talked about this. You haven't done anything with the arrays, with the data section yet. Probably next homework assignment will. Maybe. We'll see. I might have you guys do chess in assembly for bridges. We'll see. So this is how you make an array in, if you have a fixed size array in ARM32. So there's a label, so you give it a name. Remember, you can attach a label to basically anything. As I think you guys learned in Locksmith. You can attach a label to pretty much anything. And the .space directive basically says allocate 400 bytes of space. So this will allocate enough room for 100 integers. Okay. If you want to make a string, you can do it this way. So this is the Z there means it's null terminated. If you do this, that is a non-null terminated string. In which case you would need to put the null terminator in yourself. That creates a const. So you can, I was thinking about using it in the one that I just wrote today. But, so you can use bytes per integer instead of 4, so you don't have the magic number in there. Where is that? Here it is. So you can use the .eq. You can create numerical constants that way if you feel like it. But the answer is this. So that's how you make a array in assembly. It's pretty simple. Just make sure it's in the data section. So there's the code section, the data section. The other way you can do it is to do dynamic arrays like this. And so dynamic array means you're calling the operating system to give you some memory, basically. And so is it read int? So that's going to read a number like 5 or whatever. How many bytes do we want? Multiply it by 4. Aha, that's break. So that is a operating system call. Basically, I think it's part of the C library that's a wrapper around the system call. And what that will do is it'll allocate memory off. It just moves the heap pointer up, basically. And so it doesn't work very well if you're going to be dynamically allocating and deallocating, because it's not the stack, right? It just gives you more memory. So as long as you never deallocate memory, this approach is fine. The better way of doing it is to call malloc. Malloc will remember where you've allocated memory, and so you can free it, and it'll keep track of which chunks are available. And so if you allocate and you've got a chunk available, it'll fit it in there and stuff like that. Malloc is a fairly complicated function to write, as Zach DeFuria and Mr. Mueller, the people that spoke here a couple weeks ago, could tell you one of their hardest assignments was writing malloc. This code here just calls sbreak. So So if you guys remember our picture of a memory map, you got a program. Around 0, you have the minefield of doom. All right, don't dereference a null pointer, or Brett the Hitman Hart will come out and put you into the sharpshooter. Somewhere above that, though, is the code segment, and that's where your actual code is. That's usually marked as read-only and execute. You can actually tag different chunks of memory as being readable, writable, and executable. There's actually permissions on chunks of memory. And so the code segment is marked as executable, but you can't write to it. That prevents viruses. Above that is your BSS, which we'll ignore, and above that is the data segment. The data segment grows up, and then up at the very top is the stack, and that grows down. Your normal variables like int x and y, they live up here in the stack. Every time you call a function, it moves the stack pointer down. The stack pointer pointing here, you make a function call, stack pointer moves down. If you move the stack pointer too far down, you get a stack overflow error and your code crashes. The data pointer moves up. How do you move it up? Well, there's a function called sbreak. Okay. So how do you move the data pointer up? Sbreak. It doesn't move up normally. So if you want to allocate 100 megs of RAM, you say sbreak 100 megs, and it will. There's just a pointer, and it will just move the pointer up. Okay. And if you want to allocate and deallocate memory, don't try doing that yourself. Malloc. Malloc is used for that, and malloc calls sbreak. So don't. In reality, you shouldn't call sbreak. You should be calling malloc. And malloc will allocate a chunk of memory. If it needs it, it will move the segment up, and then it will return to you a pointer for wherever your array is located. Okay. Earlier you said not to worry about the fifth parameter, but you don't need to use them all. I don't think so. Like which is sentence 45 in main.cc. Just so you guys know, like a lot of this stuff you could probably not. I would not implement this one-to-one. There's a lot easier way of doing this assignment than trying to copy every one of these lines. Okay. And what I would actually do is not worry about the edge cases at all. Instead, you've got this array, right? And this array, and the way I would start as you guys is I would not start on Korea. I would make like a 3x3 map and start on that, right? And write a helper function called printInt and print the ints out. Like that thing that I gave you right there is how I would actually start this homework assignment. Start by being able to read values from a 2D array, make a 2D array that's small. Don't start with a 500 by 500 Colorado map. Hell no. This is actually a habit of mine that you guys need to get into. When you guys are doing programming assignments, you need to start small. If your code doesn't work and you're looking at 9 million numbers, like what went wrong? Right? Did you confuse the row and the column? That happens all the time. If that happens, you'll see it like at a weird angle, But you can't tell if it's a giant array. So start off with like a 3x3 array. And put in 1 and 10 and 100, just fill it with some sample things. Start really small. And then start here at this row and see if it picks out the right height to go to, right? Learning how to test your code is a really important skill in computer science. Start small and go slow. Don't write this giant thing. I would start by just printing the array. Start with the code that I just gave you guys for printing a 2D array. Just see if your assembly code can do that. And if it can do that, then you're almost done. But honestly, what I would do is rather than worry about all those edge cases with like going off the top of the thing and going down off the bottom of the thing, what I'd actually do is in C++, I'd actually just wrap this whole array here in like 99999s, things like that. And then you're never going to go off the boundary. It's an easy way of doing it. So I would just pass to it an array that, and then choose as a starting location, this would be column 1 instead of column 0, right? And then you just make all these numbers really big, and then it'll never go off the edge of the map, hopefully. You don't have to worry about all the bounce checking and stuff like that. And if you think that's cheating and that people wouldn't do that in real life, yeah. Yeah. It's called padding an array. It's very common. It's a common technique. Just make the array bigger. Okay. Secrets. So, do you guys understand that? You can do that in C++. You don't have to do that in assembly. Just pad the array. Just add an extra row and column to the top, bottom, left, and right. Set it equal to max int as the height, or a billion. It doesn't really matter. None of the elevations are that big, and then all of your edge cases don't exist anymore. All these things go away. Right. Almost all this code is just dealing with edge cases. And what's easier than dealing with edge cases? Seemingly. What's easier than dealing with edge cases? Not dealing with edge cases. That is exactly right. That is precisely it. Yeah, so just don't. Yeah, just make your code as simple as possible in assembly. Look, there's that formula again. Yeah. Okay. You already dealt with them just segfaulting? Well, if you're segfaulting, then maybe you're not dealing with them right. I don't know. Yeah. So, yeah, my advice to you guys is make a little test map. Make the file format for these maps. You should be able to figure out, right? If you look at these map files, it's the dimensions, right? So just change it to 3 by 3. Make a new map. Copy Colorado 1 to be test. I already have a test. Tiny .dat. Actually, I could just delete all that, can't I? 3 by 3, and the heights are 1, 100, and 1,000, and 5, and 50, and 20, and 10, 90, 30, right? So if I were to start on this spot right here, it should move to the right, and then it should move down right. So this is the mindset that you need to get into when you're coding. To make your own test cases, make them as simple as possible. See if you can just start off by printing the array and having it print the array correctly using that code that I gave you in Asim Demos 20. Once you got that, then all you have to do is say, all right, if I'm here, then just check that value, that value, that value, and see which one is closest to 5. Okay, it's 50, so move to the right. And you set when you move to the right, you set that elevation to be -1. That's it. And once you get to the rightmost column, you're done. That's the whole program. Okay. So, simple test cases. Make them yourself. Like make a. Maybe 1 by 1 is too small, right? That's not going to give you useful information. But like a 3 by 3, and just see if when you print the values, just see if they're coming out the way you think they are. Because if you forget like multiplying by 4, like I did, then maybe that's why you're segfaulting. Who knows? So just print the values, write yourself helper functions like. So in the 2D array thing here, I created some helper functions. You can do that for this assignment. I'm allowing it. In previous assignments, I didn't allow you to do things in C++ because I wanted you to do it in assembly. But for this one, sure, I'm allowing it. So I'm allowing simple helper functions like this to print a number, print print a space, print a new line. Easy. Just call them from assembly, see if your code's working. Okay. The hardest part about assembly is when it doesn't work, you don't know why. So finally, last thing is when you compile your code, make sure you compile your code with -G. All right, -G. If you made a makefile for this, or if you have a makefile for this, add -G to every line. That will put debugging information into the compiled executable, and then you will be able to GDB your code. Okay. So if I GDB a.out, break on main, run, right? It's got the lines of code in there. 2e enable. Next. How many rows do you want? 6. I want 10 columns. Right. So you can look at your values and all that kind of stuff. Yeah. So that's it for today, guys. The homework is due on Thursday. Like I said, one trick that you can play that'll allow is to pad the array. Just add a row up top, row on the sides, row down below, set them up to 1 billion, whatever. I wouldn't get too close to max integer because if you start adding things, it could overflow. So I'd set it to like 1 billion, and then you don't have to worry about edge cases because it will never navigate to that place. Okay. So good luck, have fun. It seems hard, but it should be medium difficulty, ideally. All right, good luck, you guys. If you have any questions, hit me up on Discord. You know where I am. All right, see you later. And I'm going to put up I guess it'll just be a daily quiz, but it'll be a bigger quiz on pipelining, just to see if you guys get the concepts from it. Okay. All right, see you guys.